Chapter 10 Atmospheric Circulation and Weather Systems. Earlier, Chapter 9 described the uneven distribution of temperature over the surface of the Earth. Air expands when heated and gets compressed when cooled. This results in variation in the atmospheric pressure. The result is that it causes the movement of air from high pressure to low pressure, setting the air in motion. You already know that air is horizontal motion as wind. Atmospheric pressure also determines when the air will rise or sink. The wind redistributes the heat and moisture across the planet, thereby maintaining a constant temperature for the planet as a whole. The vertical rising of moist air cools it down to form the clouds and bring precipitation. This chapter has been devoted to explain the causes of pressure differences, the forces that control the atmospheric circulation, the turbulent pattern of wind, the formation of air masses, the disturbed weather when air masses interact with each other, and the phenomenon of violent tropical storms. Atmospheric pressure. Do you realize that our body is subjected to a lot of air pressure? As one moves up, the air gets rarefied and one feels breathless. The weight of a column of air contained in a unit area from the mean sea level to the top of the atmosphere is called atmospheric pressure. The atmospheric pressure is expressed in units of millbar. At sea level, the average atmospheric pressure is 1000.2 millibar. Due to gravity, the air at the surface is denser and hence the higher the pressure. Air pressure is measured with the help of a mercury barometer or the aneroid barometer. At any elevation, it varies from place to place, and its variation is the primary cause of air motion, that is, wind, which moves from the highest surface pressure areas to low pressure areas. Vertical variation of pressure. In the lower atmosphere, the pressure decreases rapidly with height. The decrease amounts to about 1 mb for each 10 m increase in elevation. It does not always decrease at the same rate. Table 10.1 gives the average pressure and temperature at selected levels of elevation for a standard atmosphere. The vertical pressure gradient force is much larger than that of horizontal pressure gradient, but it is generally balanced by a nearly equal but opposite gravitational force. Hence, we do not experience strong upward winds. Horizontal distribution of pressure. Small differences in pressure are highly significant in terms of the wind direction and velocity. Horizontal distribution of pressure is studied by drawing isobars at constant levels. Isobars are lines connecting places having equal pressure. In order to eliminate the effect of altitude on pressure, it is measured at any station after being reduced to sea level or purposes of comparison. The sea level pressure distribution is shown on weather maps. Low pressure system is enclosed by one or more isobars with the lowest pressure in the center. High pressure system is also enclosed by one or more isobars with the highest pressure in the center. World distribution of sea level pressure. The world distribution of sea level pressure in January and July has been shown. Near the equator, the sea level pressure is low and the area is known as equatorial low. Along 30° north and 30° south are found the high pressure areas known as subtropical highs. Further, polewards along 60° north and 60° south, the low pressure belts are termed as the subpolar lows. Near the poles, the pressure is high and it is known as the polar high. These pressure belts are not permanent. In nature, they oscillate with the apparent movement of the sun. In the northern hemisphere in winter, they move southwards and in the summer northwards. Forces affecting the velocity and direction of the wind. You already know that the air is set in motion due to differences in atmospheric pressure. The air in motion is called wind. The wind blows from high pressure to low pressure. The wind at the surface experiences friction. In addition, Rotation of the Earth also affects the wind movement. The force exerted by the rotation of the Earth and is known as Coriolis force. Thus, the horizontal winds near the Earth's surface respond to the combined effect of three forces: the pressure gradient force, the frictional force, and the Coriolis force. In addition, the gravitational force acts downward. Pressure gradient force. The differences in the atmospheric pressure produces a force. The rate of change of pressure with respect to distance is the pressure gradient. The pressure gradient is strong where the isobars are close to each other and is weak where the isobars are apart. Frictional force. It affects the speed of the wind. It is greatest as the surface and its influence generally extends up to elevation of 1 to 3 kilometers. Over the sea surface, the friction is minimal. Coriolis force. The rotation of the Earth about its axis affects the direction of the wind. This force is called the Coriolis force after the French physicist who described it in 1844. It deflects the wind in the right direction in the northern hemisphere and to the left in the southern hemisphere. The deflection is more when the wind velocity is high. The Coriolis force is directly proportional to the angle of latitude. It is the maximum at the poles and is absent at the equator. The Coriolis force acts perpendicular to the pressure gradient force. The pressure gradient force is perpendicular to an isobar. The higher the pressure gradient force, the more is the velocity of the wind, and the larger is the deflection in the direction of the wind. As a result of these two forces operating perpendicular to each other, in the low pressure areas, the wind blows around it. At the equator, the Coriolis force is zero and the wind blows perpendicular to the isobars. The low pressure gets filled instead of getting intensified. That is the reason why tropical cyclones are not formed near the equator. Pressure and wind. The velocity and direction of the wind are the net result of the wind generating forces. The winds in the upper atmosphere, 2 to 3 kilometers above the surface, are free from frictional effect of the surface and are controlled mainly by pressure gradient and the Coriolis force. When isobars are straight and when there is no friction, the pressure gradient is balanced by the Coriolis force and the resultant wind by the Coriolis force and the resultant wind blows parallel to the isobar. This wind is known as geostrophic wind. The wind circulation around a low is called cyclonic circulation. Around a high, it is called anticyclonic circulation. The distraction of winds around such systems changes according to their locations in different hemispheres. The wind circulation at the Earth's surface around low and high on many occasions is closely related to the wind circulation at higher level. Generally, over low pressure area, the air will converge and rise. Over high pressure area, the air will subside from above and diverge at the surface. Apart from convergence, some eddies, convection currents, orographic uplift and uplift along the fronts cause the rising of the air, which is essential to the formation of clouds and precipitation. General circulation of the atmosphere. The pattern of planetary winds largely depends on 1. Latitudinal variation of atmospheric heating, 2. Emergence of pressure belts, 3. The migration of belts following apparent path of the sun, 4. The distribution of continents and oceans, 5. The rotation of the earth. The patterns of the movement of the planetary winds is called the general circulation of the atmosphere. The general circulation of atmosphere also sets in motion the ocean water circulation which influences the Earth's climate. The air at the intertropical convergence zones rises because of convection caused by high insolation and a low pressure is created. The winds from the tropics converge at this low pressure zone. The converged air rises along with the convective cell. It reaches to the top of the troposphere up to an altitude of 14 kilometers and moves towards the pole. This causes accumulation of air of about 30 degrees north and south. Part of the accumulated air sinks to the ground and forms a subtropical high. Another reason for sinking is the cooling of air when it reaches 30° north and south latitudes. Down below near the land surface, the air flows towards the equator as the easter lies. The easter lies from either side of the equator converge in the intertropical convergence zone. Such circulations from the surface upwards and vice versa are called cells. Such a cell in the tropics is called Hadley cell. In the middle latitudes, the circulation is that the sinking cold air that comes from the poles and the rising warm air and that blows from the subtropical high. At the surface, these winds are called westerlies, and the cell is known as Ferrel cell. At polar latitudes, the cold, dense air subsides near the poles and blows towards middle latitudes as the polar easterlies. This cell is called the polar cell. These three cells set the pattern for the general circulation of the atmosphere. The transfer of heat energy from lower latitudes to the higher latitudes maintains the general circulation. The general circulation of the atmosphere also affects the oceans. The large-scale winds of the atmosphere initiate large and slow-moving currents of the ocean. Oceans, in turn, provide input of energy and water vapor into the air. These interactions take place rather slowly over a large part of the ocean. General atmospheric circulation and its effects on oceans. Warming and cooling of the Pacific Ocean is most important in terms of general atmospheric circulation. The warm water of the central Pacific Ocean slowly drifts toward South American coast and replaces the cool Peruvian current. Such appearance of warm water off the coast of Peru is known as El Nino. The El Nino event is closely associated with the pressure changes in the central Pacific and Australia. This change in pressure condition over Pacific is known as the Southern Oscillation. The combined phenomenon of Southern Oscillation and El Nino is known as ENSO. In the years when ENSO is strong, large-scale variation in weather occur over the world. The arid west coast of South America receives heavy rainfall, drought occurs in Australia and sometimes in India, and floods in China. This phenomenon is closely monitored and is used for long-range forecasting in major parts of the world. Seasonal wind. The pattern of wind circulation is modified in different seasons due to shifting of regions of maximum heating, pressure, and wind belts. The most pronounced effect of such a shift is noticed in the monsoons, especially over Southeast Asia. The other local deviations from the general circulation system are as follows. Local winds. Differences in the heating and cooling of the Earth's surfaces and the cycles these develop daily or annually can create several common local and regional winds. Land and sea breezes. As explained earlier, the land and sea absorb and transfer heat differently. During the day, the land heats up faster and becomes warmer than the sea. Therefore, over the land, the air rises, giving rise to a low pressure area, whereas the sea is relatively cool and the pressure over sea is relatively high. Thus, pressure gradient from sea to land is created and wind blows from the sea to the land as the sea breeze. In the night, the reversal of condition takes place. The land loses heat faster and is cooler than the sea. The pressure gradient is from the land to the sea and hence land breeze results. Mountain and valley winds. In mountainous regions, during the day, the slopes gets heated up and air moves upslope and fill the resulting gap. The air and the valley blows up the valley. This wind is known as the valley breeze. During the night, the slopes get cooled and dense air descends into the valley of the mountain wind. The cool air of the high plateaus and the ice fields draining into the valley is called katabatic wind. Another type of warm wind occurs on the iceward sea side of the mountain ranges. The moisture in those winds while crossing the mountain ranges condense and precipitate. When it descends down the iceward side of the slope, the dry air gets warmed up by the adiabatic process. This dry air may melt the snow in a short time. Air masses. When the air remains over a homogeneous area for a sufficiently longer time, it acquires the characteristics of the area. These homogeneous regions can be vast ocean surface or vast plains. The air with distinctive characteristics in terms of temperature and humidity is called an air mass. It is defined as a large body of air having little horizontal variation in temperature and moisture. The homogeneous surfaces over which air masses form are called the source regions. The air masses are classified according to the source regions. There are 5 major source regions. They are 1. Warm tropical and subtropical oceans. 2. The subtropical hot deserts. 3. The relatively cool high latitudes oceans. 4. The very cold snow-covered continents in high latitudes. 5. Permanently ice-covered continents in the Arctic and Antarctica. Accordingly, following types of air masses are recognized. 1. Maritime tropical. 2. Continental tropical. 3. Maritime polar. 4. Continental polar. 5. Continental Arctic. Tropical air masses are warm and polar air masses are cold. Fronts. When 2 different air masses meet, the boundary zone between them is called a front. The process of formation of the fronts is known as frontogenesis. There are 4 types of fronts: cool, warm, stationary, occluded. When the front remains stationary, it is called stationary front. When the cool air moves towards the warm air masses, its contact zone is called cold front. Whereas, if the warm air mass moves toward the cold air mass, the contact zone is a warm front. If an air mass is fully lifted above the land surface, it is called occluded front. The fronts occur in middle latitudes and are characterized by steep gradient in temperature and pressure. They bring abrupt changes in temperature and cause the air to rise from clouds and cause precipitation. Extratropical cyclones. The systems developing in the mid and high latitude beyond the tropics are called middle latitude or extratropical cyclones. The passage of front causes abrupt changes in weather conditions over the area in the middle of high latitudes. Extratropical cyclones form along the polar front. Initially, the front is stationary. In the northern hemisphere, warm air blows from the south and cool air from the north of the front. When the pressure drops along the front, the warm air moves northwards and the cool air moves towards south, setting in motion an anticyclonic circulation. The cyclonic circulation leads into a well-developed extratropical cyclone with a warm front and a cool front. The plan and cross-section of a well-developed cyclone is given. There are pockets of warm air or warm sector wedged between the forward and the rear cool air or cold sector. The warm air glides over the cool air, and as a sequence of clouds appear over the sky ahead of the warm front and cause precipitation, the cold front approaches the warm air from behind and pushes the warm air up. As a result, cumulus clouds develop along the cold front. The cold front moves faster than the warm front, ultimately overtaking the warm front. The warm air is completely lifted up and the front is occluded, and the cyclone dissipates. The processes of wind circulation, both at the surface and aloft, are closely interlinked. The extratropical cyclone differs from the tropical cyclone in a number of ways. The extratropical cyclones have a clear frontal system which is not present in the tropical cyclones. They cover a large area and can originate over the land and sea, whereas the tropical cyclones originate only over the seas and on reaching the land they dissipate. The extratropical cyclone affects a much larger area as compared to the tropical cyclone. The wind velocity in a tropical cyclone is much higher and it is more destructive. The extratropical cyclones move from west to east, but tropical cyclones move from east to west. Tropical cyclones. Tropical cyclones are violent storms that originate over oceans in tropical areas and move over to the coastal areas, bringing about large-scale destruction caused by violent winds, very heavy rainfall, and storm surges. This is one of the most devastating natural calamities. They are known as cyclones in the Indian Ocean, hurricanes in the Atlantic, typhoons in the Western Pacific and South China Sea, and willy willies in the Western Australia. Tropical cyclones originate and intensify over warm tropical oceans. The conditions favorable for the formation and intensification of tropical cyclones are 1. Large sea surface with temperature higher than 27 degrees Celsius. 2. Presence of the Coriolis force. 3. Small variations in vertical wind speed. 4. A pre-existing weak low pressure area or low level cyclonic circulation. 5. Upper divergence above the sea level system. The energy that intensifies the storm comes from the condensation process in the towering cumulonimbus clouds surrounding the center of the storm. With continuous supply of moisture from the sea, the storm is further strengthened. On reaching the land, the moisture supply is cut off and the storm dissipates. The place where a tropical cyclone crosses the coast is called the landfall of the cyclone. The cyclone which cross 20 degrees north latitude generally recurve and they are more destructive. A schematic representation of the vertical structure of a mature tropical cyclonic storm is shown in the figure. A mature tropical cyclone is characterized by strong spirally circulating wind around the center, called the eye. The diameter of the circulating system can vary between 150 and 250 kilometers. The eye is a region of calm with subsiding air. Around the eye is the eye wall, where there is a strong spiraling ascent of air to greater height reaching the tropopause. The wind reaches maximum velocity in this region, reaching as high as 250 kilometers per hour. Torrential rain occurs here. From the eye wall, rain bands may radiate and trains of cumulus and cumulonimbus clouds may drift into the outer region. The diameter of the storm over the Bay of Bengal, Arabian Sea, and Indian Ocean is between 600 to 1200 kilometers. The system moves slowly from about 300 to 500 kilometers per day. The cyclone creates storm surges and they inundate the coastal lowlands. The storm petters out on the land. Thunderstorms and tornadoes. Other severe local storms are thunderstorms and tornadoes. They are short durationed, occurring over a small area but are violent. Thunderstorms are caused by intense convection on moist, hot days. A thunderstorm is a well-grown cumulonimbus cloud producing thunder and lightning. When the clouds extend to heights where sub-zero temperature prevails, hails are formed and they come down as hailstorms. If there is insufficient moisture, a thunderstorm can generate dust storm. A thunderstorm is characterized by intense updraft of rising warm air, which causes the clouds to grow bigger and rise to greater height. This causes precipitation. Later, downdraft brings down the earth to cool and the rain. From severe thunderstorms, sometimes spiraling wind descends like a trunk of an elephant with great force, with every low pressure at the center, causing massive destruction on its way. Such a phenomenon is called a tornado. Tornadoes generally occur in the middle latitudes. The tornado over the sea is called waterspouts. These violent storms are the manifestations of the atmosphere's adjustments to varying energy distribution. The potential and the heat energies are converted into kinetic energy in the storms and the restless atmosphere again returns to its stable state. End of chapter 10.